This video is going to compare two-way versus one-way ANOVA and then start with a new example using the protein data from ELC. So first off, what are the advantages of performing a two-way ANOVA when we have two categorical explanatory variables instead of using two one-way ANOVAs where we have one categorical predictor each? So I'd like you to pause this video and see if you can brainstorm a few ideas and then pick up and we'll go through this together. So some of the advantages of two-way versus one-way ANOVA is that with a two-way ANOVA as opposed to two one-way ANOVAs is that the two-way ANOVA allows us to investigate an interaction. If we have two one-way ANOVAs, we're looking at one categorical variable at a time, and that means that it's impossible to look at whether the two variables interact because there's only one variable or one categorical explanatory variable in there. Also, by including two explanatory variables in the model, we have more explained variability. Remember, every explanatory variable contributes to the explained variability. We have a better model. That means we have a higher R squared relative to either of the one-way ANOVAs with each of those variables. We also, by including the interaction term, that's an extra explanatory variable because it's an extra term in the model, so that is also contributing to more explained variability. It's not a new variable, but it is another term in the model. Remember the regression model that we looked at in the previous video. We had an indicator variable for each level of one of the categorical predictors. We had indicator variables for every level, for all but one level of another categorical variable. But then we also had all of those interaction terms. And so those interaction terms acted kind of like other variables, and they also further explain the variability. So interactions are like explanatory variables, so that is another effect in the model, and it also increases our explained variability. And so that means that we therefore have less unexplained variability. So there is only so much total variability, right? So if we think about our ANOVA table, we have explained variability for the model, we have unexplained variability for error, and those together equal the total variability. Well, if we have more explained variability, that means that our unexplained variability or our error variability must decrease. Well, if we have more explained variability, then that also means we have more power. It's easier to detect any effects that might exist. So it's easier to detect a beer main effect if it's present, because we've reduced the unexplained variability. The error variability, that mean squared error, has decreased because we have less unexplained variability. But it's also easier to detect a gender main effect than it would be in that one-way ANOVA for just gender, because there's less unexplained variability in the two-way ANOVA than there would be for a one-way ANOVA, including just gender. And then finally, because we can look for an interaction with the two-way ANOVA that we would not be able to do with two one-way ANOVAs, we're able to even test for that interaction, so there's more power to test for that interaction. So for example, let's review. When we did the one-way analysis for beer, our F statistic was 13.31. The mean squared between the explained variability for between is unchanged. The unexplained variability, however, has decreased because we have removed more variability, we've explained more variability by also measuring gender. So it hasn't gone into beer. We've still explained the amount of variability for beer. The differences between the beer group means is the same. But by also then saying, well, let's look and see what's going on between the genders and for the interaction, the unexplained variability has decreased. So for the two-way ANOVA, for beer, the F statistic, the F stat, is 20.0651. And that's just because we have less unexplained variability. That's just because we have more power. It's easier to detect the same size effect because we have included more variables, more terms in the model. So the model is explaining more by looking at gender and those interaction terms, and so there's less unexplained variability. So let's look and see with these protein data. So these protein and weight gain data are on ELC, so this is what it looks like in JUMP. So the data are a randomized experiment measured in weight gain in grams of male rats under 6 diets. So we've got the source of the protein, so it could be beef, cereal, or pork, and the level of protein, whether that was a high or low amount of protein in each of those 3 sources. So 10 rats were assigned to each of those 6 diets. So it could be a high or low protein beef diet, it could be a high or low protein cereal diet, and it could be a high or low protein pork diet. So there are 60 rats total, 10 in each of those combinations of diets. So here we have the output, and we're going to do a two-way ANOVA to compare this. We could have done 2 one-way ANOVAs to look at the effect of just the source. So if there was a difference in the beef, cereal, or pork in terms of the mean weight gain, and we could have done a one-way ANOVA to see if there was a difference between the level, whether there was a difference between the low and high levels of protein. But because of what we just talked about, the advantages of doing a two-way ANOVA, we can also look and see if there is an interaction between the amount of protein and the protein source, and have more power for looking for these two main effects as well. So what we're going to first do is we are interested for now in just looking at the interaction. So our null hypothesis is that there is no interaction between the source and level, that would be the amount of protein. So that is the effect of protein source is the same regardless of the amount on weight gain. So both of these are saying that there is no interaction. That's our null hypothesis. The alternative hypothesis, there is an interaction. When we're doing two-way ANOVA, our hypotheses are always going to be contextual or plain language hypotheses. We are not going to be writing two-way ANOVA hypotheses symbolically. It gets very messy. We have to introduce a whole bunch of new notation. So hypotheses for two-way ANOVA will always be contextual, always written in plain language. For these hypotheses to be, or in order to conduct this test, we have to check some conditions, and we haven't introduced the conditions for two-way ANOVA yet. The conditions for two-way ANOVA are exactly the same as for one-way ANOVA. So I'm going to scroll over, I apologize for that, and write them over here. So our conditions for two-way ANOVA, they should be familiar. The first is that we have independent and random samples. In this case, we have 10 rats randomly and independently assigned to each of the 6 diets. This was an experiment. They did this. So we have independent samples because there's no overlap between the groups. None of the rats got more than one diet. And we have random samples because we have random assignment. So this is satisfied because of random assignment. This is a completely randomized design. The next thing we need to have is that we have normal distribution of the response in each group. So here we're going to go and look at the output. We've got 6 distributions. We have the beef low protein group, the cereal low protein group, the pork low protein group, and then the beef, cereal, and pork high protein groups. So based on these histograms, does it seem reasonable that we have a unimodal and symmetric distribution in each of the groups? And I'm going to say, yeah, especially considering that we only have 10 observations in each group, a unimodal and symmetric distribution seems reasonable. We do have some gaps in the data, but that's just because of the small sample size. So I'm going to say, yes, each histogram is approximately unimodal and symmetric. Awesome. The third one, we have to have approximately equal standard deviations of the response for each group. We're going to go back to the output. So back and forth. Well, does it look like, and we're not given the actual standard deviations, but we could get them. So we're just going to look. So does the spread for the first group look like the spread for each of the subsequent groups? That is, because all of these are plotted on the same scale, does it look like any one group is substantially more or less spread out than any of the others? And again, I'm going to say no. They all look to have about the same spread. So here, all standard deviations are about the same. And the histograms are about the same spread. So check, we're good there. The last thing that we need is to make sure that we have a quantitative response. We should probably have checked this first. A quantitative response and 2 categorical predictors. And that has been satisfied. The response is the weight gain in the rats. And the explanatory variables are the protein source and protein level, high or low. So this has been satisfied. So we're good. We have satisfied all the conditions needed for ANOVA, or for two-way ANOVA, to be valid. So we come back over here, and now we can think about our decisions. We're interested, right, in in looking at just the interaction. So based on these these data, we have, what do you think? Strong or weak evidence for an interaction. We're looking at both the size of our p-value, the size of our f ratio, but we might want to also consider our sample size. So this is n equals 10 observations per group. We might want to also consider the profile plot that was provided, so this interaction profile plot that was provided. And we could also look at the histograms, which also shows the locations of these data. So I'm going to pause this. I'm going to ask you to pause this and think. What do you think about these, about this result? So here, we kind of have conflicting information. The F ratio is not very large. So the F statistic is 2.75. So it's saying that we have about twice as much, not quite 3 times as much explained variability by the interaction effect as we have unexplained. We also have kind of a hard to interpret p-value. So it's small. If there were no interaction, we would get something, an F ratio like this, or bigger, about 7% of the time. But it's not tiny, right? And so this is why we like to avoid that 0.05 cutoff. 0.07, excuse me. But we have clear evidence of an interaction in the plot. So for the low protein source, the red line here, this bottom line, it looks like that this, for the low protein level, it looks like the source of the protein has no effect at all. So when you go from beef to cereal to pork protein sources, when the protein level is low, the weight gain stays pretty much the same. So rats who had low levels of protein, whether they had beef, cereal, or pork, they gained about the same amount of weight. However, for this blue line, the top line, which is the high protein source, rats gained a very different amount of weight. And remember, this is measured in grams. So if rats had a high protein diet and they were on beef or pork, they gained about the same amount of weight. So no difference between beef or pork for the high protein diets. However, if rats had cereal with a high protein diet, there was about a 15-gram difference. And these are rats. So 15 grams for a rat is a big amount. So there was a big decrease in the weight gain between beef and cereal and pork and cereal, even though there was no difference between beef and pork. So what we're seeing here is that because there was basically no difference between beef and pork, and this is the only place where this interaction effect is occurring. That's why we're having kind of this difficulty telling we're having a difficulty picking up this interaction effect. So the plot is telling us one thing. We have pretty strong visual evidence, or pretty clear visual evidence of an interaction, even though the F-test is having a hard time identifying it. So, what do you think we should do? We could err on the side of caution. So I'm going to write this down. So we have our F statistic is 2.75, the p-value is 0.07, but clear evidence in the plot of an interaction. So err on the side of caution. What does this mean that we're doing? So if we say that there is evidence of an interaction based on this plot and based on this slightly elevated but not super high p-value, so this is still a lowish p-value. So if we say that there is evidence of a relationship when there really isn't one, what does that mean? It means that we would be making a type 1 error, right? So if there really is not an interaction, but we say that there is, if we err on that side of caution, we'd be making a type 1 error. But that doesn't seem so bad. That doesn't seem so bad here. And we'll talk about that in just a minute. So we're going to err on the side of caution. We're going to retain the interaction in the model. And let's think about why. Okay? So how would we choose? So if we were using a significance level, so if we were going to use a strict cutoff for identifying whether to retain or whether to reject or fail to reject a test for an interaction, how would we choose that threshold? So let's think again about a type 1 or type 2 error. So what is a type 1 error in this context? A type 1 error would be rejecting the null hypothesis of no interaction when there really is no interaction. We'd be identifying an interaction is present when there really is not an interaction. So we'd say that the effect of the source, there is not a constant effect of the protein source for the different levels of protein when the effects are really the same. So what's that consequence really mean if we're thinking about that model? It really just means we have a more complicated model than we need. We'd be including an interaction term that isn't really necessary. So a type 1 error, to repeat, is we find or say there's an interaction when there really isn't one. And the results are including a term that isn't necessary in the model. So it's a more complicated model than is necessary. Okay, so what would be a type 2 error in this case? Well, it would be removing an interaction that is necessary. So remember, a type 1 error is a false alarm. A type 2 error is a miss, right? It's omitting or missing an interaction that is actually present. So what is that impact? What are the ramifications? Right? So if the ramifications for a type 1 error is like a slightly more complicated model than is necessary, then removing or omitting an interaction and taking that out of the model, that's a loss of information. So we would remove an important part of a model and lose information about the real world. And that doesn't sound good, right? Because that's a type 2 error. And so in this case, we'd lose important information about the relationship between weight gain and the protein sources. And how that is affected by the level of protein. We're seeing here, so if we were to use an alpha of 0.05 in this case for this interaction term, and we would say, okay, well, there's no interaction, therefore we'll omit it, we'd be missing this important piece that tells us that no, having cereal at the high level of protein actually decreases that protein gain, decreases that weight gain. We'd be missing that really important piece of information. So which of these two outcomes, which of these two ramifications is more serious? Is it worse to have a more complicated than is necessary if we commit a type 1 error, or is it worse to miss an important aspect of the relationship? So which one of these two errors is more serious in this case, a type 1 or a type 2 error? I would argue that a type 2 error is more serious, so we should probably have a more sensitive test. So if we think back to the readings at the very beginning of the semester, when we've seen and read about people just always arbitrarily using an alpha of 0.05 without really thinking about the ramifications of the type 1 and type 2 errors, this is one of the possible outcomes. If you don't think about what a type 1 or type 2 error mean for a given context, and here we're thinking about even within a specific model where we might use a 0.05 significance level for the overall model, but maybe a slightly higher alpha for the interaction effect because missing that component for the model is worse, then we're not doing that critical thinking about the outcomes. That's one of the reasons why we're not using significance levels at all in this class, but we want to be mindful of how other people are operating and the decisions that they made and are probably not documenting in when they are using their significance levels in their research and their write-ups. So type 2 error is more serious. We need a more sensitive test because we want to be more willing to consider small effects like we had above. That is, use a higher significance level for interaction. So we're going to be more willing to consider smaller effects, more willing to consider higher p-values for the interaction. Because if we had just used an alpha of 0.05 here, we would miss this very important interaction term. And if there really isn't an interaction, big deal, right? We just have a slightly more complicated model. And in later classes, you would learn about different ways that we can guard against making this kind of error too often using things like cross-validation so that we wouldn't be responding just to noise in this particular data set. All right, so that is an example of two-way versus one-way ANOVA. We've looked and learned about our conditions for two-way ANOVA to be valid and how to check them. And we've talked about being a little less cautious, a little less sensitive when testing the interaction. So when we do a two-way ANOVA, we test the overall model first. So we test the overall ANOVA first, and then we test the interaction term. That is the first term we look at. And then if the interaction is useful, it doesn't really make sense to test for the main effects because why would we average the sources together if there is an interaction effect? The interaction is telling us that the effects are not the same at the different levels, so it would not make sense to average over the levels of the other factors. So if we have an interaction, stick at the interaction level and break out the levels. So we'd want to interpret the high source of protein separately from the low source of protein rather than averaging over the source or the levels of protein. So that's it for this video. We will pick up and finish chapter 14 in the last video, which is talking about how can we break out and compare these things for two-way ANOVA using multiple comparison methods like Tukey.